would look at the absolute value of the error. One of them looks at the integral of the error over time. One of them looks at the rate of the change of the error. So this is Kp, this is Kd, this is Ki. Let me just write this Ki over S, Kd times this. Okay. So if you just like were concerned about like what is a PID controller, why do we want to have P controller, PID controller, so that actually depends on each system, right? For some systems, just like a P controller might be good enough. For some systems, PI might be good enough. For some systems, you have to have PID. It depends on like how the error changes. Like there's no set formula, and there are simulation software packages that try to optimize these coefficients so that you would reach your final value faster. It doesn't mean that like anything that you put here, it's gonna guarantee that you get here, right? First of all, sometimes if you add a controller, it might make your system unstable, right? So you might just like go over this. Sometimes you might reach another value instead of this value, right? So it doesn't mean that you can just randomly pick some values, Kp, Kd, Ki, and just like put it in the controller and expect to get the perfect response. There are methods to optimize the values of these controller gains, but it's beyond the scope of the course. I just want you to have an idea that you can't just randomly pick some values and put it here and expect that your system works fine. Okay, now the part that I want to mention now, it's new, and please pay very good attention to this part. So it's related to what I was just talking about, that you might choose a controller and you expect to reach your reference value, but you might end up at a different point. Okay, so the topic that I'm gonna discuss right now, it's called the steady state error. Okay, I'm gonna use one example to show this. Let's say this is Y reference. This is positive, negative. Let's say we just like have a proportional controller with the gain of 1, right? So basically doesn't do anything, right? So basically just one feedback, and there's no sensor unit here, sensor transfer function here. And let's say this is the transfer function of our plant. Okay, so this is error, this is U. So here we measure the output, we find the error, we adjust the U, and then we feed it towards our transfer function. So let me just write down some equations in the S domain. So the E, okay, I just want to find like Y of S. Y of S is error times 1 times 1 over S minus 2, right? So it's like GP of S times GC of S, GP as F just times GC of S times E, which is Y reference minus Y. Okay, is everybody okay with this? Y ref minus Y becomes E. You multiply it by GC would become U. Multiplied by GP becomes Y. This is what we have. Okay. Let's just like put what we have here. So Y reference minus Y. I just like didn't write the S variables here. Times 1 over S minus 2 is equal to y. Let's actually, okay, let me just write this, and now I'm just gonna write this as y times s minus 2. Okay. Let's take a Laplace transform, inverse Laplace transform of this one, because these are in the S domain. If I take the inverse Laplace transform, we're going to go to the time domain. So this is going to become y ref of t minus y of t. This is the instantaneous error, is equal to s times y of s. What is the inverse Laplace transform of that? That's right. It's going to be dy over dt, right? The derivative of output minus 2 times y of t. Okay. Is everybody okay? So like this is what we ended up with in the time domain. Okay. Now, and the steady state, assuming that this is a stable system, at the steady state means that when t goes to infinity, there's no changes in our variables anymore. There's no changes in our parameters anymore, right? So it means that dy by dt is going to be equal to 0 at t equal to infinity. Okay, as t moves towards infinity. This moves towards 0, right? Because that's the definition of a steady state. It means like all the oscillations would basically get damped, or like would just basically like we reach a point that there's not much change here. So the derivative of our response with respect to time, it basically tends to 0. So at t equal to infinity, let me just remove this, erase this. At as t tends to infinity, we would have y ref minus y is equal to negative of 2 negative 2y. Actually, I could have made this a little bit simpler. I could have just write this one as y ref minus yt is equal to this. This would have been better. So y ref, actually no, that's okay. Or like let's just like leave it like this. Y ref becomes equal to negative y. If t moves to infinity, our output, it's gonna be negative of y reference. Isn't that crazy? We wanted to reach this point, but based on the closed loop system that we have, at infinity we're gonna reach negative y ref, right? So this is called steady state error. Means the difference between y and y reference at